Yes, welcome to DC Economics. So today I'm going to take you through introductory part on probability. Have you heard the word probability? Actual probability is the basis upon which the discipline of statistics has been developed and applied in many fields associated with the chance of occurrences, such as issue of politics, business, weather forecasting, and scientific research. Probability may be taken as a tool with which we may solve the problems involving uncertainties. In fact, uncertainty is the basic element of human experiences. We tend to examine assumptions that we don't know exactly what will happen in the future. So such examples may be issues of travel time, a number of customers, rainfall, temperature, share price movement, length of our life, and etc. So actual probability is calculated, is obtained under specific terms, some that it does not exceed 1 to given specific terms. So probabilities may be taken as a tool with which may solve the problems involving uncertainties, as you observe. There are three approaches to understanding probabilities. We have three approaches: classical approach, empirical or frequency-based approach, and what is known as subjective approach. Classical approach, this approach traces back to the field where probability was first systematically employed, which is the gambling or flipping coins or tossing dice and so forth. Gambling problems are characterized by the random experiments which have any possible outcome equal or likely to occur. The number of observations, total number of sample space over total number of observations of a given data. But also, it means that none of them is more or less likely to occur than other one, hence they are said to be in a symmetrical position. So the idea of the classical approach is that given a collection of k element out of the total number of observation any, that the probability of occurrence of the event E is represented by the collection that is k over any. That is 0 less than or equal to k and less than or equal than any. Let's come to the second approach that is known as empirical based frequency approach. This approach was formally introduced in the field of the natural science where the assumption of symmetric positions are poor fails. So instead, the idea on which this approach is based is that the several experiments that can be run under the certain condition are considered as equivalent. So each experiment might lead either to success or to an insuccess. So here now, we suppose we have the any random experiments run under the equivalent condition. We define the frequency of success, which is event E, that is given as a function of the event E number of success in experiments over not total number of any total number of observations. So we consider the empirical law of change, which is said that the more stable the frequency becomes, we can conclude that the limit of the frequency for any that is greater or infinite does not exist and is equal to the probability of that event success. So under this approach, the number of an event is given by the number of success in experiments over n, as you observe. So here, any random experiment run under equivalent condition, as you can observe, that we given the probability that is the limit of the total number of observation E, taking the infinite to the f any respect of number of event E. So let's come to the difference between the frequency-based empirical approach and classical approach. Then now let's look by example. Imagine that you want to know the probability of outcome of outcome that is toys. When you want to look on, you start looking on the base of classical approach. Since the possible number of outcomes are 2 that are head and tail, the probability of A will be given as 1 over 2. So for empirical approach, you can several times, let's say, if you start tossing a coin several times, let's say 100, out of your attempts, you will obtain 55 head and 45 tails. Hence, the frequency of the event head is 55 over 100, which give you 0.55. And it can be approximate probability of the event of the head. So you can see we have obtained the two different probabilities, that is 0.5 versus 0.55 for the same event. So the key difference is the rule of information after 100 experiments you have gathered. So empirical evidence that heads occurs or more often than the tail. So subjective approach developed the probabilities by B definite. This is the most intuitive definitions of probabilities. So under subjective approach, this approach tends to explain the probability of an event is the degree of belief a person attaches to that event based on his or available information. So this reason holds only under the assumptions of rationality, which assume that people act coherently. That every individual, every player every agent in the economy acts to max highest potentiality. That is a behavior of coherence that we call rationality. So some of the basic concepts in probability include the sample space, the event. Sample space is a set of all possible outcomes of an experiment. Event is a subset of a sample space. So to find the probability of an event, we need to count the numbers of outcomes of that event and the number of all possible outcomes of the experiments, and then divide the former by their rates. So some accounting rules, for example, let's try to look at an example. The items are selected at a random from a manufacture process. Each item is inspected and classified differently, as you can observe. Then none is defective. So you're required to solve out what will be the sample space from this scenario over here. So we need to identify the defective that is represented by D and non-defective represented by N. So the sample space that we address here will include DD, because we don't know exactly what kind of sample will be taken since the individual inspected and classified on defective and non-defective. So we take out DD. This is item selected. We do not know exactly what was selected. So we take out DD as the first selection as a probability. DDN, DDND, NDD, DNN, NDN, NND, and NN. So as you can observe, this is double N. Here there is double N, NN. So as you can observe here, the sample space will take in this category. Since we do not know exactly what we are selected. So maybe select on the first part DD, then second part DDN, then third part DND, then NDD, then DNN, then NDN, NND, and NNN, as you can observe. So this is actual would be our sample size. So our total sample size is presented by taking out this value over here. So the total sample size, the total sample space selected randomly from a manufactured process would include DDN, DND, NDD, DNN, NDN, NND, and double N, as you can observe. So let's come to example number 2. Now, from our above data for the sample space that we have obtained, that is DD, DDN up to NN, we require to find out the event, the number of defectives above or greater than 1. Now, when we apply solution here, we take out the probability of an event of number of events over total number of sample space. So we identify the number of events. So since we are working on how the number of defective above greater than 1. So we consider to look where there is DD, that are 2D, not only 1D to our sample space. Then that will be identified as the number of an event. So the number of defective be greater than 1. This means that we consider to take out DDD. We consider to take out DD, then DDN, then D and D together with NDD. But other values like D and N and DN will not consider them because they are not greater than 1. So this will be the number of events will be DD, then DDN, then ND, then NDD, as you can observe. So this the total number of events will be taken equals to 4, as you observe. So the total number of events will be equals to 4. Now we consider what will be our total number of sample space. Total number of observations. When we consider the total number of observations, this means that we take all the values without isolating them from what is greater than DD. So this will be 8. 1, 2, 3, 4, 5, 6, 7, up to 8. So divide by 8. So the probability of an event of defective that is above or greater than 1 is equal to taking 4 divided by total number of observations, that is 8. So the answer here will be equals to 1 over 2. This will be our probability, as you can observe. So the total at the event that the number of defectives are above greater than 1 would be equals to 1 over 2. So when you take out divide 1 by 1 over 2, this will exactly give out in decimal places that is equal to 0.5. Example number 3. Suppose a reference spread contains 2 letters following by 3 digits, with the first digit not 0. How many different reference spreads can be printed, as you can observe? So we have the number of choices for the first letter, second letter, and the first and second and third letter, but the 3 digits with the first digit is not equal to 0, as you observe. So how do we obtain the number of different reference spreads that can be printed? From our data set, and from our data set we observe to take out 26 from the first letter, we times 26 from the second letter, and we times 9 as well as 10 in the second letter at between and at the end letter of 10, as you observe. So this means that the number of different reference spreads that can be printed is like to say we take out 26 times 9 times 10, then times 10 exactly. So we take out, this will give out 26 brackets times 26, then times 9, then times 10 bracket, then times 10 again. So when you use your calculator, this will give out 608400. So that will be the answer. That will be the answer from our question. So the number of different license plates that can be printed is equal to 60,8400, as you can observe. So let's look to another question. Find the possible permutations, the number of ways where the sequence of the letters is counted from 3 letters A, B, and C, as you can observe. We're required to find the possible permutation, the number of ways where the sequence of the letters is counted from 3 letters A, B, C, as you can observe. Now, solution. We have the total number of letters, that is ABC. This means that the number of letters are taken, these are the 3 letters you can observe. So the number of permutation is given by any permutation divided by bracket any minus R permutation. So we have the total number of observations, that is 3, and we have also the rate of letters, number of letters, that is given is R. So we have R, which is equal to 3. So when we plug into our formula, to our data set, this will give out, this is like to say it will take out 3, then we take out CDP, that is base of 3 is equal to 3 permutation divided by 3 minus 3 permutation. So when you divide here, the answer will be equal to 6. So the number, when you try to find the possible permutations, the number of ways where the sequence of the letter is counted from 3 letters A, B, C, when you divide 3 permutation divided by 3 minus 3 permutation, will give us exactly equals to 6. So the general formula we apply is number of observation PL, 3 permutation divided by 3 divided by 3. As I told you, it gives out 6, as you can observe. So that is how we perform such kind of question. Let's go to another example. Let's consider another example so as we can widen out the knowledge on math solving the permutations. Example number 4. Find the number of 3 letters words formed from 5 letters. So we have the total number of letters, that is any, which is equal to 5, as you can observe, and we have the R, that is equal to 3 letters. So from our formula, number of permutations, we take out any permutation divided by any minus R permutation. So this like to say we take out 5, P, then base of 3 is equal to, we take out exactly 5 permutation, divide by 5 minus 3, then permutation. So the answer will be equals to 60. So you use your calculator to solve the particular question. You obtain the answer which is equal to 60. So the number of 3 letters words formed from 5 letters. So the number of 3 letters words formed from 5 letters give you equals to 60. Let's look another example. For example, you are required to find the possible permutations of the following 5 letters. That is A, B, C. So they're almost 5 letters. So the number of letters here 5. But remember, we need to take, when you identify the error, we need to identify the number of letters that are not repeated of the given general letters. So for that case, our error will be equals to 3, and we take out the total number of observations. We take out our n will be equals to 3, and we take out the 5 letters, permutations for the 5 letters, the given sample data that we have. So our r is equal to 3 and our n is equal to 5. So let's plug into a formula of permutation, that is PR base of r is equal to any permutation divided by any minus r brackets permutation. But here, what we do here, we take out the number of observation, any permutation divided by r permutation, that gives you 5 over 3 permutation. So this is simple, we can solve. We take out 5 permutation divided by 3 permutation. That will give you exactly 20. So that will be the answer. So after looking, so let's try to look on another example. How many 7 letters words can be formed using the letters of the word benzene? How many 7 letters words can be formed using the letters of the word benzene? So what we do here, we consider to take out the number of any to identify the number of letters. So we have 7 letters, that is benzene. But remember, from the word benzene, there are some letters which are repeated. They're almost 7, but there are some of the letters are repeated. They are, for example, instead of B, we have only a single B. We have only a single B from our way benzene. But when you consider to look on E, we have almost letters E, which is equal to 2 letters of E, as observed. But also we have also the word any. N is repeated also. We have 2 N. So we have almost 3 E. The E are repeated 3 times, and N is repeated 2 times. That is N, which is equal to 2. And Z is only single. So Z is equal to 1. So that's identify the values from the numbers that are repeated. So in order to calculate, to understand, to examine how many letters words can be formed using the word benzene, is where now we take out the values we take out the 7 letters that are not repeated. We take out the total number of letters that is equal to 7. So we take out the 7 permutation. We divide by the number of letters that were not repeated. We times them in form of permutations. That we take 1 permutation times 3 permutation times 2 permutation, then times 1 permutation. So this will give you, the value will be equal to 7 permutation divide by, we take 1 permutation, then times bracket, then times bracket 3 permutation bracket, then times, you put bracket 2 permutation, then bracket times, then 1 permutation, then bracket, which will give you, when you set it in the calculator, it will give you 420. So in your calculator, if you want to click permutation, you click on the upper side of logic. You click shift, then you click logic. The upper side, you obtain the permutation. So we may conclude now the number of the number of letters that can be formed using the letters of the word benzene will be equals to uh, 420. That will give you exactly 420. So the number of letters that form the word benzene will be equals to 420. Now, after saying so, let's look on another example. So let's try to look on the concept of combinations. In the past examples, we have looked on how we apply permutation more at large. But next part, we're going to look on how we could apply the combinations and find the number of combinations, the number of ways where the sequence is not counted. So number of combinations, that the number of ways where a sequence is not counted of n distinct objects taken at r at a time that is given by any, is then any combination based of r is equal to any permutation divided by r permutation times bracket number of any divide minus r bracket then permutations. So this is a formula that we apply in combinations. So we take out any combinations as we observe. These are the any combinations as that we apply into a formula. For that case, let's look at an example. Find the possible combinations of 5 distinct objects taken 3 at a time. Find the possible combinations of 5 distinct objects taken 3 at a time. So what we need to consider there, when we consider to take out our formula, the number of combinations, that is CR is equal to any number of combinations divided by R combinations, brackets, then number of observations, N divided minus R computation, then permutations. So what you need to consider here from our combinations formula, we take out any SR is equal to any permutations. Then R divided by R permutation, bracket any minus R, then permutations, as you can observe. So our n is equal to 5 and r is equal to 3. So we set out our data set, as you can observe. Let you plug 5 to our formula. This will be equal to 5 based on combination of 3, which is equal to, now we set out 5 there, divided by 3, then times, then take out 5 minus 3, then bracket, then permutation. So when you divide over there, that will exactly give you 10. So that will exactly give you 10. So that is the answer. Let's look on another example. So that was example number 1. Let's look on another example. Example number 2, what is the number of 3 persons committee that can be formed from a group of 4 persons? Solution. So from combination, we take out any, then combination divided by R, then bracket, then any minus r, then permutation bracket, as you observe. So the number of r is equal to 3 and number of n is equal to 4. So this will be 4, then combination 3 is equal to 4 divided by 3, then brackets 4 minus 3 bracket, then permutations, as you can observe. So let's divide over there to obtain the answer. So the answer will be equals to 4. So that is how we perform the question. So the number of 3 persons committee that can be formed from a group of 4 persons is equal to 4. So this will be equals to 4. So after solving, so now let's look on another example. So another example, this is example number 3. Let's consider, for example, let's consider another example that we tend to find out the probabilities of the events that may occur at the single part sides and the two sides as well. A box contains 8 eggs, 3 of which are rotten. 3 eggs are picked at random. Find the probabilities of the following events. A. Exactly 2 eggs are rotten. B. All eggs are rotten. C. No egg is rotten. How could you solve this? Solution. A box contains 8 eggs, 3 which are rotten. 3 eggs are picked at random. So there are 3 eggs which are picked at random, but in the box there are 8 eggs, 3 which are rotten. And we require to find the probability that exactly 2 eggs are rotten. Part A is about exactly 2 eggs are rotten. So let's go to solution. What you need to understand from this question is that if 8 eggs were rotten, if in the box there were 8 eggs, 3 which are rotten, means that the unrotten eggs, the eggs which were not rotten were only 5. Since when we take out 8 minus 3, give us 5. And actually, since we are dealing with exactly 2 eggs are rotten, this means that we need to consider the total number of eggs that were in the box. So the total number of eggs that were in the box were 8 eggs. And the 3 which were picked. But throughout, from what the 3 eggs were picked, the question has not identified anymore which kind of eggs were picked that were unrotten eggs or not rotten eggs. So since we have the box contain a total of rotten and unrotten eggs that give you 8 eggs. So 3 eggs were rotten as it mentioned in the question. So since 3 eggs were rotten, this means that we consider to take out the value of 8. We take out 8 minus 3 to obtain 5 eggs which were unrotten. So this means that we take out 8 so we'll take out 3 eggs from which were rotten, And when we to find the unrotten eggs, this means that we take out 8 minus 3. We obtain 5, which were unrotten eggs, as I told you. So we take out 8 minus 5, minus 3 to obtain 5. So this would be the unrotten eggs, as you can observe. So the rotten eggs will be equals to 3, and unrotten eggs, which is equal to 5. So in order we can obtain the exact 2 eggs which are rotten, this means that we need to consider the probability of an event over number of event over total number of sample space. So we need to find out the number of events whereby we take out, we obtain eggs, Z eggs rotten, whereby we need to pick out 2 eggs from the first group of 3 eggs from the total units of rotten eggs, and we need to take out only 1 egg from the second group that was unrotten eggs. So this will give out now, we apply the combinations in solving the particular question. So the number of outcomes would be equals to, this will give out 3, then a combination 2. Since we take the 2 eggs from the first group of 3 rotten eggs, since we are finding the eggs which are rotten, times 5 combination from the first another group. That another group is unrotten eggs, so that's what we are finding because this is unrotten egg. So we take 5 combination 1, that will give you exact 15. So this is the total number of sample space, as you can observe. So what next is need to find the total number of observation, the sample space from our data set. So the total number of sample space, total number of observations here will give you 8 combination 3, since there were 8 eggs in the box. So when we take it into the calculator, we obtain 56. So after doing so now, let's take probability of an event is equal to number of event over total number of sample space. This will give you now, this will be equals to 3 combinations, 3 combination 2, then equals to times 5 combination 1, divide by the total number of sample space, that is 8 combination 3, that will give you 15 over 56. So the answer, we may conclude similar, we may conclude that the total number of probability of an event for exactly 2 eggs are rotten exactly 15 over 56 is equal to 15 over 56. Let's come to B. We're required to find the probability of an event for an outcome that eggs are rotten. So since we are dealing on the side of rotten eggs, the total number of rotten eggs were 3 and unrotten ones were 5. So this means that the number of event over total number of sample space, this will be given the rotten eggs. We need to consider the side of rotten eggs that were 3. So the total number of sample space will be equals to 3 combination 3. It will be equals to 3 combination 3, since n is equal to 3 and r is equal to 3. Then we times 5 combination 0. So we put bracket, then we times 5 combination 0. So inside of, we put combination 0, since we are not dealing with the eggs which were rotten. We need those 3 pigs eggs that were all rotten. So this will give you 1. Divided by the total number of sample space, that is 8 combination 3. So the answer will be equals to number of events, that is 1, divided by total number of sample space, that is equal to 1 over 56. So the probability of an outcome of an event for all eggs are rotten is given by 1 over 56. Now let's come to part C. Required to find the probability of the events that no egg is rotten. No egg is rotten. That was the part C. Now, since we need to find the number of eggs that is not rotten, no egg is rotten, meaning that those three picked, those selected eggs, none was rotten. This means that the number of rotten eggs were 3 and number of non-rotten eggs were 5. So since we are dealing with the three, with all eggs that were rotten, no egg is rotten. This means that we are dealing with non-rotten eggs. The total number of event over total number of sample space will be given as taking out number of event will be equals to, it will be equals to 3 combination 0. This means that in the side of the first group of rotten eggs, we not consider to take anything since we are not dealing with rotten eggs. We are dealing with all eggs to be rotten. So we take out 5, then times combination 3. On the second group, we put combination 3 since it's the side that they were rotten, non-rotten eggs. So the total number of sample space is equal to NCR, that is 8 combination 3. So the probability will be equals to 8 combination 0 times 5 combination 0 combination 3 divided by the total number of sample space, that is 8 combination 3. So the answer will be equals to 10 over 56. So this is like when we simplify, the probability of having no rotten eggs will be equals to 5 over 28. Will be equals to 5 over 28. So that is the answer, and that's mark our end. I welcome you to other session. Don't forget to subscribe on my channel. This is DC Economics. Bye bye.